All right, before we do some examples of calculating partial derivatives of functions that are maybe a little more complicated, let's first just quickly recall from the last video our definitions of partial derivatives. Remember, we learned that the partial derivative of a function, so first maybe let me write up in the corner here. We're going to let f of x, y, this is our function of two variables. Partial derivative of this function with respect to x was the limit as h approaches 0 of f of x plus h, y minus f of x, y all over h. And then we had a definition for the partial derivative of f with respect to y, and it was the limit as k goes to 0 of f of x, y plus k minus f of x, y all over k. Right, and remember, instead of using these as like the working person's definition of derivative, what we can do is adapt kind of a lot of our derivative rules from the single variable setting to help us actually compute derivatives much faster. So remember, so recall, to compute partial, use single variable derivative rules in I'll say the appropriate variable, right? But it's whichever variable you're looking at the derivative with respect to. So in, I'll say respective variable, and then treat all other variables as constants. Okay, and this was kind of our method of calculating partial derivatives in a much more timely and concise way. So let's do an example. Let's find, so if g of xy is sine of x squared y minus 2x plus 4, let's find partial derivative of g with respect to x, pardon me, and the partial derivative of g with respect to y. All right, so let's first remember, these are, I'll stop emphasizing the notation, but maybe one last time here. I'll really emphasize that the partial derivative of g with respect to x can also be written in the notation g sub x of xy. And we want to find partial with respect to x and partial with respect to y, which can be expressed as g sub y xy. Okay. From now on, I'll use these interchangeably without justification. But again, I wanted to emphasize one more time that these are indeed the same. So let's calculate partial derivative with respect to x. Well, this is d dx of sine x squared y minus 2x plus 4, right? And so now we are treating y as a constant and using our single variable derivative rules for the variable x. And so what do we have to use here? Well, we have a function inside of the trig function here. So that means we need to use the chain rule, right? And the chain rule says you take the derivative of the outside times the derivative of the inside. And so what's the derivative of the outside? Well, the derivative of sine is cosine, right? And you leave the inside the same. So x squared y minus 2x plus 4. And then this is times the derivative of the inside. And since we're taking the derivative with respect to x, this should be times the partial derivative with respect to x of the whatever's inside the sine function, which is x squared y minus 2x plus 4, right? And so I'll calculate this derivative first here. Well, the partial derivative of the term x squared y, we're taking the derivative with respect to x. and y is a constant. And so that means we're going to have a derivative of this term as 2xy, right? Because it's a power rule in x, but y is a constant. And then looks like we'll have 2xy minus 2, derivative of negative 2x with respect to x is 2, derivative of constant 0. So we have that, and then it was times cosine x squared y minus 2x plus 4, right? And so here's our partial derivative with respect to x of the function g of xy is sine of x squared y minus 2x plus 4. Let's calculate the y partial derivative, g sub y of xy. Well, this is going to be the partial derivative with respect to y of sine of x squared y. I already forgot the function. Minus 2x plus 4. Okay, so again, we have the chain rule, but now it's in the variable y, and x is the variable that we're treating as a constant. So the derivative, using the chain rule here, the derivative of sine is cosine of x squared y minus 2x plus 4. Whoops. And then times, the chain rule says, then we have to take the derivative of the interior function here, which is x squared y minus 2x plus 4. Right? But again, since this is the partial with respect to y, when we do the chain rule, we need to make sure when we take the derivative of the interior function, it's the derivative with respect to y. And so now you can see, well, x is a constant. And so when we take the partial derivative with respect to y of x squared y, the x squared can be pulled out from it because it's constant. And then the derivative of y is just 1 with respect to y. So it's going to be x squared. And then it looks like the derivative of negative 2x plus 4 is going to be 0 because there are no y's in there, right? That entire expression, negative 2x plus 4, is constant with respect to the variable y. So this is just x squared cosine x squared y minus 2x plus 4. And this is our partial derivative of the function, but with respect to y now instead of with respect to x. And so now you can get an idea of how it's a little bit different flavor for each variable that you're taking the partial derivative, right? Sorry, this should be in parentheses there. That was misleading that I did not include that in parentheses. Right, because it was this derivative times the cosine thing. Okay. So I think now, to get an idea of some more examples, let's look at partial derivatives in for functions of 3 variables now. Partial derivatives for functions of 3 variables, right? And so again, right, now what we have is some function w equals f of x, y, z here. And this is a function of 3 variables, which means the domain is R3, right? And so the graph of this function is going to be in 4-dimensional space, so we can't really picture it. But we still, what we need to do is understand how this 3-dimensional hypersurface is, how is it changing in the x direction? How is it changing in the y direction? And how is it changing in the z direction, right? Again, you know, if this was dimension 4, you'd have something orthogonal to all 3 of these, right, in some dimension w. And we'd want to see, how is the function changing with respect to x, y, and z? Well, we get similar definitions. So we have partial derivative of f with respect to x is defined to be the limit as h approaches 0, right? It's the same idea where you take, now it's a surface and not just a curve, right? you take a surface where x and y are held, or excuse me, you take a surface where y and z are held constant, and then you look at how this surface is changing in the x direction, right? And so this is f of x plus h, y, z. I'll erase some of this. Minus f of x, y, z all over h. And then partial derivative of f with respect to y is a limit as k goes to 0 of f of x, y plus k, z minus f of x, y, z all over k. And then we would now have partial derivative of f with respect to z, which is the limit as, say, like m goes to 0 of f of x, y, z plus m minus f of x, y, z all over m, right? And so we would have these limit definitions for now partial derivatives of a function of 3 variables. And we can still use our rule here, right? We treat, you know, when we're looking at how a hypersurface is changing in the x direction, we hold y and z constant. So say this is y and z and x here. We hold y and z constant, and we find the slope of the tangent line. Well, when you hold y and z constant, right? So what is a surface? What I was saying earlier is what a surface is when you hold one variable constant, right? If I were to hold just y constant, and then I get some surface, like in this picture, it's a vertical, right? It would be like a vertical surface here. And it's how am I changing in the x direction? How am I changing in the z direction? But then once I fix z as well, I get some curve. And it's okay, well, how am I just changing in the x direction now, right? And so what that means, though, is, again, when we're taking the partial derivative with respect to x, we geometrically are holding y and z constant. And so that means when we calculate the derivatives, these partial derivatives, we can hold all other variables, or we can treat them all as constants as well. So let's do an example. Let's find all partial derivatives of f of x, y, z is the function x squared y minus 4xz plus y squared all over x minus 3yz. All right, and so we want the partial derivative with respect to x. So what's f sub x? X, y, z. Right? So we have to take the partial derivative of this whole thing with respect to x. And this is a quotient of two multivariable functions. And so since we're using, or since we understand that we can take the derivative with respect to x by holding y and z constant, this means we have to use the quotient rule, right? But this is with respect to the variable x. So if we do this, we'll get, so the derivative of the top over the bottom. And so let's just write this out first. ddx of x squared y minus 4xz plus y squared times the bottom, x minus 3yz, right? And to reiterate that that's not the derivative of the product, it's the derivative of the first term times the second term, right? And then it's minus the top term, so x squared y minus 4xz plus y squared times the derivative of the denominator, and then it's all of this over the denominator squared, right? This is the quotient rule. And we're using the quotient rule in the variable x, where y and z are treated as a constant. And so how about, let's simplify this a little bit. Well, the derivative of the first term, we have partial derivative with respect to x of x squared y. So I'll go back and forth a little bit here. The partial derivative of x with respect to the term x squared y. Well, y is a constant, and then we take the, we just use the power rule in the variable x. So the derivative of x squared y with respect to x is 2xy. We have, whoops, we have then minus 4xz. Well, z is also a constant with respect to x, and the derivative of 4xz with respect to x would just be minus 4z. Then we have plus the derivative with respect to x of y squared. We know that's a constant, and the derivative of the constant is 0. So that term is 0. So we get 4xy minus 4z, or 2xy, excuse me, minus 4z times x minus 3yz. And then that was minus, we had x squared y. Okay, so it was the numerator of the function, which was x squared y minus 4xz plus y squared, right? And then this was times the derivative with respect to x of x minus 3yz. Well, the derivative with respect to x is 1, or the derivative of x with respect to x is 1, and then we have the derivative with respect to x of negative 3yz. Y and z are both constant, so that whole term is a constant, which means its derivative is 0. So this derivative was just 1, so times 1. And then all over, it was the denominator squared, so x minus 3yz squared. And now we could simplify this slightly. We can FOIL these two terms here. So we'd get 2x squared y minus 6xy squared z minus 4xz plus 12yz squared, and then minus x squared y minus 4xz and then minus y squared all over x minus 3yz squared. This should be plus, excuse me, right? Because it's a minus, and then negative should distribute. So it should be plus. And it looks like our answer should be 2x squared y minus 6x y squared z. These cancel. Plus 12yz squared minus, okay, so we do have one term we can simplify here. We have 2x squared y, and then we have minus x squared y. And so what that would equate to is me simply removing this 2 out front. So we have xy squared there, and then there was minus y squared all over x minus 3yz squared. And this is the partial derivative of the function with respect to x. Now, we are finding all partial derivatives. So that means next we need to find the partial derivative with respect to y. And so I can save a lot of work here. This is now, we're trying to find the partial derivative of f with respect to y. So it's partial derivative of this quotient function with respect to y. And notice I still have to do the chain rule, right? But it's, or not the chain rule. I still have to do the quotient rule, but now it's in the variable y, right? And so I can simply replace this df dx with, or ddx with ddy, and I can use the same quotient rule here. And so now I'm taking the derivative of the numerator here with respect to y. And the derivative of x squared y is going to be, with respect to y, is just going to be x squared. So let's start over here. So we have derivative with respect to y of x squared y, which we said was x squared. We have the derivative with respect to y of minus 4xz. Well, x and z are both constant with respect to y, so that derivative is 0. And then we have the derivative of y squared, which is 2y. So we have x squared plus 2y times x minus 3yz minus the numerator, right? The numerator was x squared y minus 4xz plus y squared. Squared y minus 4xz plus y squared, right? Yeah. And then it was times the derivative of x minus 3yz with respect to y. Well, we see the derivative with respect to x is going to be 0, or the derivative with respect to y of x is going to be 0. And then the derivative of the second term looks like we'll get negative 3z all over the denominator squared, x minus 3yz squared. We can again do some simplification here. We get x cubed minus 3x squared yz plus 2xy minus 6y squared z minus x squared y minus plus, sorry, 4x z minus y squared. And all of that is times negative 3z. So let's simplify that here. So we have plus 3x squared yz. Then it looks like we're going to have minus 12xy, or sorry, xz squared. And then it looks like we're going to have plus 3y squared z all over x minus 3yz quantity squared. Do I have any simplification? Yes. I have minus 3x squared yz plus 3x squared yz. Are you going to be it? No, I have a negative 6y squared z plus 3y squared z. And so that's going to be, well, I have x cubed plus 2xy minus 3y squared z minus 12xz squared all over x minus 3yz quantity squared. And so here was my partial derivative of the function with respect to y. And let's do this one more time so we can get the partial derivative with respect to z, right? So now, so I could have saved that, but it was a little messy, so I think I'll clean it up here. Let's take the partial derivative of f with respect to z. Now, we're using the quotient rule again, right? So it's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. But remember, this is the derivative with respect to z. So all of these partials, and when we do the quotient rule and all that, it must be the partials with respect to z. And this whole thing is over the denominator squared. So let's take the derivative of x squared y minus 4xz plus y squared. Well, we can see that the derivative of this term will just be minus 4x. Right? Because the terms x squared y and y squared are constant with respect to the variable z. Right? And this is times x minus 3, I believe you were 3yz, yes. And then minus the numerator, which was x squared y minus 4xz plus y squared, times the derivative with respect to z of x minus 3yz, which is minus 3y, all over denominator squared 3yz quantity squared. Well, we get negative 4x squared plus 12xyz minus x squared y plus 4xz plus y squared. And then we see that, well, so again, let's just kind of factor these both at once here, or distribute these both at once here. So it looks like we're going to get plus 3x squared y squared, and then minus 12xyz plus 3y cubed all over x minus 3yz squared. So we do see some cancellation, 12xy minus 12xy, and I believe that's it. So the partial derivative with respect to z is negative 4x squared plus 3x squared y squared plus 3y cubed all over x minus 3yz quantity squared. So notice that calculating partial derivatives, even with treating other variables as constant, can still be a bit tedious, but it's very good to get familiar and comfortable with calculating partial derivatives of some more complicated functions, right? And so I wanted to go through a complete example of finding all partial derivatives of a function of 3 variables. And so now that we've are starting to get more comfortable with how to actually compute them, let's talk about partial derivatives of higher order. So let's look at second order partial derivatives. Right? So remember, in the single variable case, what we had was, you had f of x, take the derivative, you get df dx. You take the second derivative, you get, the notation was d squared f dx squared, right? Or we wrote df dx as f prime of x, and we wrote the second derivative as f double prime of x, right? And so this was the second order partial derivative in the single variable setting. Well, now, what about second order partial derivatives? Well, let's start with our function f of xy. We can take the partial derivative with respect to x, or the partial derivative with respect to y. The resulting functions are df dx. I'll write that more central. Df dx and df dy, which we know we can write this as f sub x. We can write this as f sub y. But now, for second order partial derivatives, df dx is still in general, it's a function of 2 variables still, right? And so we still have to take partial derivatives. And so that means here, we can again take the derivative with respect to x and the derivative with respect to y. And what we get is, for df dx, there are 2 second order partial derivatives. we write, if you take the partial derivative with respect to x twice, notice if you follow this arrow and then this arrow, we took the partial derivative with respect to x twice, we write partial squared f partial x squared. And if we take the derivative with respect to x first, and then the derivative with respect to y, this is partial squared f partial x partial y. And then we can come over to the other side of this little diagram here, and we can take the partial derivative with respect to x of the partial derivative with respect to y, or we can take the partial derivative with respect to y of the partial derivative with respect to y. And if we do that, we get d. So the partial derivative, if you go first partial derivative with respect to y, then partial with respect to x, you get d squared f dy dx. And then if you take the partial derivative both times with respect to y, you get partial squared f partial y squared. And now we have some similar notation here. We denote the partial derivative, the second partial derivative with respect to x twice as f sub x, x, right? So we took the partial derivative with respect to x, and then we're taking that partial derivative with respect to x, but we just write that as f sub xx, right? Okay, and then that means this partial derivative first with respect to x, and then the second order with respect to y would be f sub xy. If you went first y, then x, it would be f sub yx, and then you would have f sub y, y. Right? So that's off the page. Here, let me make that a little better. F sub y, y. Okay, and so here, for a function of two variables, there are 4 second order partial derivatives, depending on, right? Because there's 4 different combinations of your x's and y's, right? You can do x twice, or you can do x first and then y, or y first and then x, or y twice, right? Those are the 4 possibilities. And so you can see then if we had like f of x, y, z, well, then you'd get well, let's just write it out. You'd get f sub x, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Well, then what are the second order? Well, then you have 3 choices, right? Then you have partial derivative with respect to x twice, or first x and then y, or first x and then z. And for the partial derivative with respect to y, you have the same thing. So you could do, this would be f sub yx, this would be f sub yy, and then f sub yz. And then second order here would be f sub zx, f sub zy, and then f sub z. And so if it's a function of 3 variables, there are 9 second order partial derivatives. So if you have to calculate all second order partial derivatives for a function of 3 variables, you have 9 partial derivatives to compute. Well, 12 because you have to find the first partial derivatives first, but there are 9 second order partial derivatives. So you can see the more function or the more variables you get, the more second order partial derivatives you get. And this goes for as many times as the function is differentiable, this keeps going, right? So if you had like f sub xx, well, then there's third order partial derivatives. There's f sub xx, the explicit third order partial derivative, and then like f sub xxy, and then f sub xxz, right? And then f sub xy. Then you can have f of xyx, f of xyy, f of xyz, and you can keep going. And so that like there's a lot of third order partial derivatives, right? And that can keep going for as however many times your function is differentiable. And so that's an idea of second order partial derivatives. Now, there is a really nice theorem that I'd like to give, but first I want to go over an example. So let's find all second order partial derivatives of f of xy is the function x e to the negative 3y plus sine 2x minus 5y. Okay, and so to find all second order derivatives, well, we have to find first order derivatives, right? What's the derivative with respect to x of x e to the negative 3y? E to the negative 3y is constant with respect to x. And so the derivative of a constant times x is just a constant. So we get e to the negative 3y. Then we have to use chain rule here, but in the variable x. So we get, looks like it's going to be plus cosine of 2x minus 5y, but we have to take the derivative with respect to x of the inside, which is 2. Okay, and now that we found f sub x, we can find f sub x. Let's start with that one. Right, which is the derivative of f sub x with respect to x. Well, the derivative of the first term is constant. E to the negative 3y is constant with respect to x. So that term vanishes. And then so we're taking the derivative of 2 cosine of 2x minus 5y with respect to x, right? And so the derivative of cosine, well, there's a 2 out there, so negative 2 sine derivative, so sine of interior minus 5y, then times the derivative of the inside, which is times 2, so this would just become a 4 out front, right? And then what's the other second order partial derivative for f sub x? Well, it's f sub x y, and so now, right, this is f sub x. So this is what we're taking the partial derivative of, but with respect to y. And so if we take the partial derivative of f sub x with respect to y, we see for the first term we get negative 3 e to the negative 3y, and then minus, well, it's going to be sine 2x minus 5y because of the chain rule, and the derivative of the inside with respect to y is just negative 5. But it's negative 5 times 2, so it's going to be minus another negative, which is plus 5 times 2, which is 10. And so this is the partial derivative, or the second order partial derivative, first with respect to x and then with respect to y. Okay? So what I'd like to do here is maybe copy the function down on this page and then do the same thing for the y derivative. So f of x y was x e to the negative 3y plus sine, it's not a very good y, sine 2x minus 5y. Okay, now what's f sub y? Well, x is constant with respect to y, and so we're just taking the derivative of e to the negative 3y. So it's negative 3, but there's still an x there, e to the negative 3y. And then by the chain rule, this is going to be negative 5 cosine 2x minus 5y, right? Because the derivative of the sine function is cosine, and then the derivative of the inside with respect to y is just negative 5. And so now we want f sub y x, which if we take the derivative of the first term with respect to x, well, negative 3 e to the negative 3y is all constant. So the derivative of x is just 1, so we get negative 3 e to the negative 3y. And now, looks like we're going to have sine, right? So it's minus the derivative of cosine is negative sign, so that becomes a plus. There's a 5 out here, so sine 2x minus 5y. But it's times the derivative of the inside, and the derivative of the inside is negative 5. So we have 5 times negative 5, which makes the constant out front negative 25. Right? Sorry, this is with respect to x. Let me back up. All right. This is with respect to x, right? And I took the derivative with respect to x here, but then I took the derivative with respect to y here. So let's not do that. I want the derivative with respect to x. So this is minus, the derivative of cosine is negative sine, so this becomes plus 5 sine 2x minus 5y. The derivative of the inside with respect to x is 2, so this is plus 10 sine 2x minus 5y. There we go. I like that a lot better. So then we can calculate the second partial derivative with respect to y both times, right? And now we're taking the derivative of this function with respect to y, which looks like it's going to be 9x e to the negative 3y. And then here we have derivative of cosine is sine. That becomes so plus 5 cosine 2x minus 5y. And here's where I want the derivative with respect to y, which will now make this negative 5 times 5, so minus 25. And so I've now calculated all 4 of my partial derivatives. Now, I actually want to use my mistake earlier to bring something up. How did I catch that that was a mistake? I caught that that was a mistake because if you'll notice, the partial derivative, the second order partial derivative, first with respect to y and then with respect to x, if you examine the result, it's the same as the partial derivative with respect to x first, and then the partial derivative with respect to y. And what made me catch the mistake is that these are different. There's actually a theorem that says the partial derivative, the mixed partials are equivalent. And so this is no mistake that f sub xy is the same as f sub yx. And that's how I caught that I made an error, because I said, okay, well, this isn't the same as what I calculated here. And so I knew something was wrong. And that leads me to this theorem for f of xy continuous. So I'll say on the domain D, f sub xy is equal to f sub yx. And this is equality of mixed partials. Right? And so here was a first example verifying this theorem, is that f sub yx was indeed the same as f sub xy. And so, you know, when we're first calculating partial derivatives, you'll want to verify this quite a bit. But once we're comfortable with them, you know, that saves us computing one partial derivative because we know they'll be the same. So we can compute, maybe one is easier than another to compute the partial derivatives. And so we stick with computing the easier one first. Okay. And so this theorem is where I would like to end our introduction and discussion about partial derivatives. Certainly we'll be using them for the rest of the course, and there are a lot of applications of partial derivatives, and we will start to take a look at some of these applications. The first place we'll go is coming up with equations of tangent planes and linear approximations.